Hello and welcome to this movie about special relativity. There are various other movies made about it on YouTube, but none that really concentrated on geometry and the treatment of this subject as a linear transformation. So this movie is intended to address these issues. I'm going to start off with treating the unit values of time and length as unit vectors, giving them names. The unit vector of length in the x direction of space will be called I. That's a name that it already had, but I'll give the unit vector of time another name, t hat. I've decided to adjust these two vectors so that the speed of light will be 1. If the unit time vector is 1 second, then the unit length vector will be 300 million meters. But I could just as easily have defined the time unit to be 1 nanosecond and the length unit to be 10 centimeters. I just want to concentrate on the geometry and not so much on the numbers. If we consider a nice clean linear transformation like rotation, where an object with 1 unit in the x direction slowly becomes 1 unit in the y direction, without its length ever being changed, then this is a very everyday, observable and familiar transformation, and it is a very nice and clean way to mix the various direction vectors. And it is orthogonal, since it preserves angles and lengths. Stretching is also an everyday linear transformation, being used when somebody stretches a spring or rubber band. It isn't orthogonal because lengths aren't preserved. It operates in only one dimension of length. Now if we look at the special relativity transformation, also called a boost transformation, for a considerably high velocity of 0.7 c, we firstly notice that the time vector rotates by approximately 40 degrees. This represents its timeline or world line as it journeys through space, where the distance travelled by a spaceship changes linearly over time. This would be the case with Newtonian mechanics too, without special relativity. But in that case, the length unit vector would remain unchanged. In special relativity, two other things happen. The first thing is that the unit length vector rotates by the same angle as the time vector, but in the opposite direction. It moves towards the time axis. Another thing to notice is that the unit vectors lengthen, so there is mixing of length and time, and more than what is let on by the variable gamma that's always associated with special relativity. This linear transformation is very nasty looking. It doesn't preserve angles or lengths, and as we'll see, it stretches vectors very long in one direction and squeezes them a lot towards the speed of light line. And it doesn't lend itself to hand-drawn pictures because people often underestimate the amounts that the unit vectors are stretched and squeezed. Here is this transformation with a low speed for relativity, 0.1 c. Even though gamma is close to 1, the amount of mixing that is occurring is already quite high, being about the order of 0.1 units. Here, for a velocity of 0.4 c, even though it gives a fairly low gamma, the mixing is quite high, having 0.5 of t added to I. The vectors are stretched longer than gamma. The tilting of the unit vector I causes there to be a great change in simultaneity. Travelling 1 unit forwards in distance causes you to travel about 0.5 units into the future. Simultaneity breaking occurs quickly and significantly compared to things like time dilation and length contraction, because the direction of the unit vector I represents all event points that occur at the same time. Having a look at a high velocity like 0.9 c, we see that the unit vectors have been stretched a lot, and squeeze towards the speed of light line, the positive one. The transformation is trying to make them point in the direction of the speed of light. It's also trying to expand them out so that they will become very long. If they are very long, say thousands of times as long as the initial unit vectors, and they are squeezed together very tightly, then they are, in a sort of way, the speed of light, or good approximations to it. This is the transformation for 0.95c, and the vectors are much longer and more squeezed compared to the original unit vectors. Here is the transform for 0.99c, and the two new vectors are hard to distinguish from each other, even in a computer drawing. Notice that we had to scale the unit vectors I and t to be much smaller so as to fit these other longer unit vectors on the screen. Now to study time dilation. Supposing that one time unit is a second, then the fast spaceship will have moved forwards in time, in 1 second, by about the pink coloured vector t dash. What is this amount of time measured by the observer who is standing still? Drawing a dotted line from the end of this vector towards the time axis will give an answer of gamma units, which is about 1.4 units or seconds. This dotted line represents all the event points that are simultaneous to the observer at rest, because they are in the direction of his I vector. So a time of 1 second for the observer in the fast spaceship is equal to 1.4 seconds for the observer at rest. So time dilates for the observer on the spaceship compared to the observer at rest. But can this be done in reverse? According to the philosophy of relativity, the observer in the spaceship can be said to be at rest, and the observer standing on the Earth is travelling away from him. So the observer on the Earth's time would dilate compared to the spaceship. Can this be shown geometrically? Well, one way to do it is to take the endpoint of the spaceship's time vector and project it onto the t-axis with a dotted line that's parallel to its own length vector, which contains all the event points that are simultaneous in its own frame of reference. This causes the line to intersect the t-axis at 1 over gamma, which is about 0.71 units or seconds. So according to him, it's the observer on Earth that has his time dilated and not him. So how do we get around this paradox? If the spaceship decides to turn around and come home, someone will have lost or gained time. Well, the paradox is easily resolved, because for the spaceship to return home will mean that it will have to accelerate, involving the theory of general relativity, which means that the observer on the spaceship will have had his time dilated without any contradiction. This time dilation in special relativity is an observer-dependent thing, and doesn't have any real meaning if neither of them ever change their velocities. And what about length contraction? Is it the same sort of thing as time dilation? Well, not really. It is based on what the observer sees. If he could see the ship all at once quickly as it passes by at high speed, then he'll see all the events on his line of simultaneity, of all the event points that occur at the same time for him. In the case of the observer at rest, this occurs parallel to the x-axis, or his own I unit vector. If the ship travels fast, its front will tip into the future, because its line of simultaneity will be parallel to its own I unit vector. If it is 1 unit long, supposing 1 unit of length is 20 meters and 1 unit of time is 6.67 nanoseconds, then it will tip along its own I vector, so it could be represented by an I unit vector. The world line of its back would be along its own t-unit vector and go through the start of its i-unit vector. This world line would be represented by the thicker dotted line. The world line of its front would go through the tip of the front of its i-unit vector and be parallel to its t-unit vector, and is represented by the thinner dotted line. Its length as observed by the observer at rest would be equal to the line that's parallel to its I vector, as it starts at the world line for the back of the spaceship and end at the world line for the front of the spaceship. This length is shown by the line labelled x equals 1 over gamma, which is the solution because x has contracted. The spaceship, being of 1 unit of length, is observed to be of 0.71 units. This is because the observer at rest is seeing the front of the spaceship at about 0.9 units into the past, compared to the back of it. I hope this makes sense. The geometry is all in the unit vectors. But will the observer on the spaceship see the Earth contract? The answer is yes, as it can be seen by the geometry. If a structure on the Earth is aligned with the velocity of the spaceship and is 1 unit in length, then the I-unit vector can represent this object. The t-axis is its world line at the back of it, represented by the thicker dotted line, and the thinner dotted line that runs parallel to it and that runs through the front of the structure's I vector is the world line at the front of it. The length observed by the spaceship crew member would equal the line that runs parallel to his I-axis between the two world lines. This is equal to 1 over gamma of its own I vector, so he sees lengths contracted and not dilated. And this is because apparent lengths depend on the direction of simultaneity of the different observers. Well, I hope you found this useful. It is a good idea to watch other YouTube videos on relativity and come back to this one every now and then until you feel that you can understand it. Good luck on your study of special relativity.